Good afternoon, ladies and gentlemen. I'm Ding Jiatong from Shanghai Jiao Tong University. Today, I'm honored to present our research DSMC investigations of aerodynamic drag and heat reduction for hypersonic rarified flow around bluff body. This study focuses on addressing the challenges of aerodynamic drag and thermal management of hypersonic spacecraft operating in rarefied atmospheric conditions during re-entry process. By simulating different configurations with open-foam software, we can figure out effective and feasible drag and heat reduction strategy. Generally, my presentation will be divided into 5 parts: introduction, methodology, configurations, results and analysis, and the final conclusion. The first part is about introduction. As everybody knows, heat and drag reduction has always been a heated topic in the research. With the advance of space technology, the space launch mission has become more frequent, from 114 times in 2018 to 233 times in 2023. These were carried out by hypersonic vehicles such as rockets. When operating in atmosphere during the re-entry process, hypersonic vehicles encounter severe aerodynamic heat and drag in atmosphere, requiring heat and drag reduction scenario. Their configurations can be described as bluff body, characterized by their blunt leading edges, which are often used in spacecraft design to mitigate extreme heating. This design helps to distribute the heat load more evenly across the vehicle's surface, reducing the risk of localized overheating, meanwhile reducing the drag posed on spacecraft. The main cause of heat and drag around bluff body is the flow around bluff body. While operating under hypersonic conditions, the free stream forms shock wave around the bluff body. The shock wave not only poses considerable drag on the configuration, but also heat up the surface of bluff body through conduction, radiation, and convection. However, while extensive studies exist for supersonic flows around bluff bodies, there is limited research on hypersonic flow in rarefied conditions. Rarefied gas flow, which Knudsen number is larger than 10, cannot be described by Navier-Stokes equation as continuous flow. Therefore, we should employ both main equations to describe the rarefied flow. Active flow control techniques such as aerospikes, opposing jet, and forward-facing cavities have been effective in continuous atmospheric conditions, but are not well validated in rarefied hypersonic regimes. These techniques involve manipulating the flow field around the vehicle to reduce drag and heat transfer, such as pushing away the bow shock around the configurations, thereby improving the overall performance of the vehicle. Aerospike, above all, is one of the most commonly used scenarios. In this research, we focused on aerospikes and its relative mixture scenarios, such as aerospike opposing jet scenario, aerospike aerodynamic disk mixture scenario. The second part is about my methodology in this research. In this research, we employ DSMC foam solver in open foam. Let me introduce about the DSMC method. DSMC method, its full name is the Direct Simulation Monte Carlo method. It was introduced by Grammy Bird in 1969. It is utilized to model the rarefied gas flows. It solves the Boltzmann equations by simulating particle collisions and movements. This approach is suitable for flows with high Knudsen numbers. To conduct simulations based on DSMC algorithm, the computational space will be first divided into hundreds of thousands of blocks. The computer will simulate the collision of particles in blocks one by one every time step, based on the collision model selected, which will be a variable hard sphere model, VHS, in this research. Another part is about how to measure the heat and drag reduction ability of configurations. In this research, we selected several indexes. They are heat transfer rate, pressure coefficient, total heat transferred, and total drag. The QW represents heat transferred on unit area. The rho infinity represents the density of free stream. The V infinity represents the speed of free stream, and the P infinity represents the static pressure of free stream. The third part is about mesh and particle density verification. To ensure the accuracy of the results, we performed mesh independent and particle density independent verifications. The simulations were conducted using various densities of mesh and particle to test whether the moderate density can handle the computational process with minor errors. This step is crucial because the accuracy of DSMC simulations depends on resolving the flow field with sufficient detail, especially in regions with steep gradients such as shock waves and boundary layers. Here we employ the basic configuration to conduct verification under free stream of 8 Mach. The following are figures shows the verification results. For different density of meshes, the heat flux transfer rate and pressure coefficient have slight differences, about 3 to 6% compared with results under moderate density. For different density of particles, this ratio is about 1% to 3%. After the verification, we proved that the moderate density mesh density and particle density are capable of simulating the flow of free stream accurately. The next part is about configurations and conditions. In this research, we suppose that spacecraft is operating at the top of mesosphere, about 80 kilometers from the Earth. The environment temperature is about around 200 Kelvin. The detailed settings are as follows. The environment temperature is 195 Kelvin. The Mach number will be from 6 to 20 Mach. To simplify the simulation process, the gas composition will be 78% nitrogen and 22% oxygen by volume fraction. Under 195 Kelvin, the speed of 1 Mach is 279.25 meters per second. The next part is the introduction to our configurations. Due to the symmetric feature of blood body, here we study 2D configurations. However, OpenFOAM only accepts 3D configurations. To satisfy our needs, we set the height of the configuration to 10 micrometers, which can be nearly ignored. Here we developed 4 configurations. The first one is a basic configuration, which is a bipyramid based on the design of Daimler-Benz Aerospace Company. This configuration better suits inner design of spacecraft and is more realistic than hemisphere configuration. The second configuration is an aerospike scenario. In this scenario, we set the length of aerospike to 300 millimeters, the 1.5 times of the width of the front of the bipyramid. According to a study led by Japanese scientist Mootama, under continuous flow, while the ratio between the length of aerospike and the width of the head of the bipyramid falls between 1 to 2, the scenario significantly reduces drag and heat. The following 2 scenarios are 2 mixture scenarios. The first scenario is an aerospike aerodynamic mixture scenario. Professor Zhu et al. Studied the drag heat and reduction efficiency of aerospike aerodynamic scenario under continuous flow, pointing out that peak value of static number St and static pressure was reduced by 19% and 22% compared with aerospike scenario. Another scenario is an aerospike opposing jet mixture scenario. The opposing jet will be sprayed out from the top of the aerospike at a speed of 2 Mach. As for previous studies, Professor Geng et al. Simulated the configuration under 3 Mach of continuous flow, pointing out that the drag reduction efficiency increased from 41% to 58%. Here we want to test whether the 2 mixture scenarios are still effective or not under hypersonic rarified free stream. Then comes our result part. The first section is about the heat and drag reduction efficiency comparison under 8 Mach. From the contour, we can discover that compared with the original configuration with aerospike, the high temperature flow fields are scattered and smaller size in the 3 drag and heat reduction configuration. For the 3 drag and heat reduction configuration, the climax temperature also decreases from approximately 22,000 Kelvin to 1,800 Kelvin compared with the original configuration. This indicates that the temperature of the flow around blood body decelerates. For the three scenarios, the climax of heat transfer rate did not appear at the stagnant point of the nose cone, but at the latter point of the nose cone. This is because the free stream is diverged and pushed away from the model by aerospike before reaching the surface of the configuration, and forms a shock wave that prevents the front of the nose cone from interacting with violently compressed and high internal energy air. Then the reattached shock wave interacts with the surface, creating a high temperature zone in the latter part. Moreover, the climax of heat transfer rate and the total heat have both significantly decreased in the 3 drag and heat reduction scenarios, demonstrating that they are capable of reducing heat on a free stream of 8 Mach in rarefied conditions. Compared with other scenarios, the aerospike aerodynamic scenario is most effective. The following graph shows the climax heat transfer rate of aerospike. From the graph, we can conclude that the opposing jets greatly reduce the heat concentration on aerospike, which may increase its longevity. Then comes the drag reduction part. Pressure coefficients of different configurations can be seen in the following graph. From figure, we can discover for the original configuration, the climax of pressure appeared at the stagnant point of the nose cone. For drag and heat reduction configurations, the climax appeared in the latter part of the nose cone. For all the configurations, the heat climax point correlates with the pressure climax point. This can be explained that by the reattached shock wave has not only thermal effects on the configuration, but also post pressure on the configuration. Generally, the pressure coefficient falls in the interval between of 1.6 to 0.3. Among all the configurations, the aerospike aerodynamic scenario is the most effective in reducing the total pressure, and it is about 60%. The next part is section 2, about the heat and drag reduction ability of three configurations on different speed of free stream. The first configuration we're going to discuss is aerospike. From the figure, we can know that the total heat reduction ability ranges from 44% to 35%, and is at a constant decrease as the speed of free stream increases, except from 10 to 12 Mach. This can be explained that as the speed continues to rise, the energy of air molecules increases, reducing the aerospike's ability to push away the bow shock away. The total pressure reduction rate ranges from 4.1% to 77.75%, which is not very fundamental in real operations. The pressure reduction rate of aerospike scenario is relatively low, about 4% in low hypersonic free stream, but it increases to 77.5% around 10 Mach and becomes stable. As for the climax heat reduction, the rate is highest about 60 in the flow of 8 Mach, about 64%, and gradually decreases to around 53% in the flow of 18 to 20 Mach. Then we were going to discuss about the aerospike aerodynamic mixture scenario. From the figure, we can conclude that the total heat reduction rate of the mixture scenario reaches climax on a free stream of 8 Mach, and then constantly decrease, ranging from 54.7% to 51.03%. It's conspicuous that the total heat reduction ability of the mixture scenario is better and more stable. This can be explained that the aerodisc placed in front of the aerospike further diverged the free stream and pushed them away from the configuration. The tendency of the total pressure reduction rate of the scenario with regard to speed is similar to that of the aerospike scenario, reaching their climax at around 12 Mach and become stable. In relatively low speed free stream, around 6 Mach, the drag reduction rate of mixture scenario is only 1.6%, smaller than the aerospike scenario. However, as the speed of free stream continues to rise, the drag reduction ability of mixture scenario violently increases and surpasses the ability of the aerospike scenario. This can be explained that in higher velocity of free stream, the benefit of pushing the bow shock away further overwhelm the disadvantage of larger windward surface. The climax heat transfer reduction rate is synchronized with that of the aerospike scenario, but also better and more stable. Finally, we are going to discuss about the aerospike opposing jet scenario. From the figure, we can know that the total heat reduction ability of aerospike opposing jet scenario ranges from 37% to 90%, which is relatively lower than the first two scenarios, and decreases more violently as the speed of free stream increases. The pressure reduction rate of this scenario reaches climax about 5.7% around 8 Mach, remains stable between 8 to 10 Mach, and gradually decrease to 2%. The climax heat reduction rate ranges from 55% to 26%, which reaches its climax at 8 Mach and gradually decreases. Compared with the drag and heat reduction ability in continuous flow, the drag and heat reduction ability of the aerospike opposing jet scenario greatly decreased. Finally, there is the conclusion part. By studying the flow around bluff body and three drag and heat reduction scenarios in rarified hypersonic gas flow, we have the following conclusions. The first is that all the three configurations employed in this research can effectively reduce heat on the surface of configuration, ranging from 18% to 72% in different scenarios and under different environments. However, as the speed of free stream increases to 14 to 20 Mach, the heat reduction ability of the three scenarios all decrease. Whether their ability will further decrease can be investigated in future studies. The drag reduction abilities of the three scenarios are relatively inconspicuous, ranging from 1.6 to 9.7%. However, the drag reduction abilities are stable under high velocity of free stream, ensuring their effectiveness in real operations. In the speed of 6 to 20 Mach, the aerospike mixture scenarios have the best reduction ability, no matter total heat transfer or climax heat transfer at a certain point. The advantage of aerospike opposing jet scenario lies in reducing the climax heat flow on the surface of aerospike, increasing its longevity. And compared with former studies conducted under continuous flow, the heat reduction rate of the three configurations remain conspicuous, but the drag reduction rate greatly decreased. This might be related to the different feature of continuous flow and rarified flow, and it can be further studied. In the last, there is an invitation from a mentor. He is now an editor, a guest editor at an SCI journal named Applied Science, and he is now opening a special issue called Hypersonic Combustion, and he is welcome everyone to send draft of thesis to him. And that's all my presentation. Thank you very much, and I'm open to all your questions.